But in particular for this workshop, I think more than 6 years ago, I think Ben and I were at Columbia University at a workshop also on trustworthy AI. And that's when I realized that we're both working on this topic, but from different perspectives. And I absolutely loved what Ben had to say at that workshop. And I think her research and her work, particularly on this area of veridical data science, is very well aligned with the goals of this workshop. And I think it also brings a very nice design perspective for trustworthy AI. So please join me in welcoming Ben Yu.
Thank you. Thank you very much, Sanjit, for including me in your community. And maybe I'll give a little background on where I come from. Maybe in that context, you can see my kind of career trajectory. So actually, I did my PhD here in statistics. I was a pure math major at PKU before I came. And then my thesis was information theory and theoretical machine learning. And then I got into signal processing. I went to biolabs for a couple of years. And then I came back and went really into remote sensing, basic interviewing research. The last 10 years is more biomedical research, work very closely with domain experts, ER doctors and cardiologists. And then recent time, I've been coming back to theory more through deep learning theory, try to understand. And as Sanjit said, we have come up with this term called veridical data science. Actually, the term came up because I was at a workshop and statistics chair Tian Zheng was saying that your talk has too long a title. We need something short and sweet like machine learners. And later she sent an email saying, how about veridical data science? So Tian Zheng was really the reason I have this title. Veridical means truthful. And it's a proper English word, but it's not really used a lot. So it's actually all started from that workshop when we're there together. Yeah. I'm actually also a scientific advisor at the Simons Institute. So this is what I said. I'm really a statistician, both applied and theoretical, and a data scientist. And this is a typical, we believe data science underneath a lot of the machine learning AI development. It's not everything, but covers a very foundational corner. So what does veridical means in data? VDS is verified truth. That's what it means in Spanish. And I like to say that now we have two meanings. We want to get truthful data-driven results, but we also want to be truthful to the data science process. Like the whole how do we get this truthful result? So the paper came out with my former student like now 5 years ago called Veridical Data Science. It's a very ambitious program, both philosophical and conceptual and practical, to guide data science, and also with rigorous documentation. Because the context cannot be explained away with X and Y. You need to really bring the context. ER doctors or cardiologists, they have different languages and different judgment calls. And we want to build a trustworthy data-driven pipeline. And you can maybe say like verifiable, to use the terminology of this workshop. But as in Sanjit talk already, you have to deal with uncertainty. There's nothing like deterministic here. So why did I start on this path of veridical data science? Has been like the last 10, 12 years. I was really motivated by a lot of exposure of the so-called replication crisis about 15 years ago, where two industry groups in oncology, cancer research, try to duplicate landmark findings, and they only get 11 to 20% replication rate. And this replication crisis is getting more attention, but the crisis in a way persists. And we still have not a great replication rate in cancer research, especially for biomarker development. Fast forward 10 years later, 73 independent research teams of social scientists try to test the same hypothesis about whether immigration would lead to positive and negative support in different countries in the world for social science policy, for social policy. And the teams were given the same unprocessed data, so they have to process it, and they make different decisions, and they get the result from very large negative effect to very large positive effects. It's just because the choice of teams. And they did vet these teams. Similarly, in biology, right? Two data sets in ecology and evolution biology, same data, different analysts, and then they get different sizes. So this is really seeing the human judgment calls, even they're all well-trained, at least team as the organizers, the human judgment calls is really important source uncertainty that hasn't been considered traditionally. And data cleaning, if you work on data, at least in the statistical domain, 60 to 80% of the time, you really try to clean the data, so-called, process the data. And we try to mimic this in a class I teach in Berkeley, a PhD level class with all the helpers I have. This is an ER doctor. So Aaron got ER doctors for each team of these 3 teams of students chose to work on this data. It's about whether a kid in an ER room with traumatic brain injury possibilities, whether this kid should be sent for a CT scan to really detect whether it's bleeding. And CT scan is radioactive. So you want to minimize that. So you don't want to send too many, but you don't want to miss bleeding. That's life-threatening. And the 3 teams end up with 3 different clean data sets. And one team just cleaned away 23% of data. I did the same exercise in my current class, master class. There's a team also threw away 23%, 25% of the data. So you can see that then you had the validation, all the clean data, you get a very different view about what's going on. And Omar, my TA, we came out, we have the same guidelines, but they're in narratives. They're not mathematics, right? You say you do this, you do that, but it's in language. And we created more data sets for this problem in terms of sensitivity. That's the people who really needed CT scan get it. You want that to be high. It's not accuracy matters in medicine, it's sensitivity and specificity. It's the people who don't need it, you don't want to give it to them. And for that particular analysis, the estimate of sensitivity vary by 10%. And if you bootstrap one clean data set, you get a similar sensitivity. This says that it's substantial, this uncertainty from data cleaning. So judgment calls, again, yes.
Just wanted to understand that. So for different people doing data cleaning, produce different data sets. Yeah. Is that what is happening? Yeah. And that's the uncertainty?
Yeah.
Okay.
Yeah.
Thank you.
This analysis that we use the same machine learning method because there's also a choice of method. Here, this is only looking at the data cleaning step. So data science is really not just one step, right? We often talk a lot in academia, especially modeling algorithms, but all these things, it's a whole system. So I like to see data science as a whole system. And every step of the way, human is engaged and they make judgment calls. And you might get different conclusions, right? Which data you're going to use? Open data set, how you're going to collect it? And how do you clean it? And here we have many, many, many choices, right? Randomized algorithm, hyperparameters, supervised learning, we have a whole salute of algorithms, all of that. And we introduce uncertainty. And that's something we at least first evaluate, and then we want to control. So we need trustworthy uncertainty quantification, just not any, because we often have error bars, but it's not trustworthy, they can mislead. If too narrow, you give overconfidence, too large, you're really not ready to make a decision when you should. So you need trustworthy uncertainty quantification. And so far, most of the time, it's traditional statistical framework. We have a stochastic model. We're supposed to describe how data is generated, but we often do very limited empirical checking. It's just often come pulling out of a hat, and then we take a lot of the uncertainty very seriously. And judgment calls a huge source of uncertainty. So now I'm ready to propose a PCS framework called predictability, computability, and stability. Completely predictability, completely is taking 2 important ingredients for machine learning. Statisticians always did prediction, but it was not the center at statistics. So machine learning really took a very important problem and kind of made things pretty accessible and simple and put computation at the heart. Like 20 years ago, I jumped into machine learning. And stability is really a huge expansion of the traditional sample-to-sample variability so that we're more trustworthy or faithful to the sources and certain that, oh, there's only after you have clean data, you do a probabilistic model, that's uncertainty. So for the rest of my talk, the first part, before the break, I will say a bit more about PCS framework and documentation, because the context has come in. And actually, this is recent work. We have uncertainty quantification now. And compared with the conformal inference, which got a lot of attention, we actually do better, actually reduce the size by 20%. It's actually a new form of conformal inference. And then I'll give you a case study where how PCS framework, PCS ranking have helped reduce the cost of a possible new clinical cancer detection of prostate cancer. We're applying for patent with a group of oncologists from Michigan. And after the break, I'll get deeper into using this principle to devise new machine learning algorithms and solve a cardiology problem that's validated by experiments. And the only theory we have, of course, this is certification verification, is we come up with a reasonable regression model and we prove something. And I'll leave with some open question. I think how can we bring interest from this community to help us verify something. Okay, so as I said, the framework was taking these three principles with my former student, now I use CSF. And I use stability, it's really robustness. The reason I use that is because robust statistics has a very particular meaning. And I try to avoid that. And also in numerical analysis, control theory, people talk about stability. So it's try to build a big tent. So all these different things can be considered relative to a reasonable perturbation of the whole data time life cycle and relevant metrics, and not just one. You should have three. So we did some COVID and death prediction. We use three metrics for county level: the absolute difference of death count, relative difference, and the square root of difference, so that all our method will work well for three different metrics, because we don't know what the county officials will think which one is relevant. And it's really an attempt to unify and synthesize and expand the ideas and best practices from machine learning and statistics. You probably all heard of Leo Brahman's paper 25 years ago called One Culture, two cultures. And we try to build one culture and a uniform platform for further development. So it's a really evolving framework and principles I think will stay. Predictability is really be expanded. We started from supervised learning, right? That's where the big success machine learning. Now it's expanding in the book. I'll mention for unsupervised learning, it's become really a stand-in for reality check. I couldn't change it to R because PC has been used. And S is really about perturbation. Could be adversarial, could be just reasonable, and you make the case, right? I have a phone somewhere and I drop it, doesn't break. But if I go to the top of the floor, I drop it, probably breaks. So the context matter. For me, I cannot sue Apple for dropping my phone from top of the floor. But here, I might have a case if I have witness. So the context matters a lot. And that's the documentation. And after you assess this, you write the document, say, these are the reasonable perturbation I want to do, also constrained by computing power. You cannot do all possible perturbation, you never go home. And then you argue for stability metrics, then why you want to evaluate this. And then to improve, you might want to aggregate results to get more stable results, and context and documentation. So I fell in love with stability principle about 10 years ago. I had the opportunity to give a 2-key lecture for the Berkeley Society. And I was working on lasso for neuroscience problem. And somehow the students from Jack Gallan's lab, I was working in Jack Gallan's lab here, recorded data for 1 hour and 50 minutes. I thought that's weird. Why not 2 hours, right? We like hours. And it just occurred like, if I actually record it for 2 hours, do I get the same conclusion? And the lasso is actually not very stable when you do selections. So that was the first work. We added stability to select the parameters for lasso. And then Tukey is really doing robust statistics, right? He was really perturbing the models. I said, well, they should be coming together. So that's why I was a modeler. I was not thinking about anything about the whole pipeline. It's like a reproducibility manifested in the stability of statistical result relative to reasonable perturbation to data and to the master model. So try to unify sample perturbation with model perturbation. And over the last 10 years, I realized stability is really at the heart of many, many things. And even for problem formulation, you need to have linguistic stability. When I was a graduate student, ML meant maximum likelihood. Now it's machine learning. So you can see the meaning of words also change over time. And matrix for us is a table of data. If you talk to a cancer researcher, matrix means a microenvironment, a biological structure. So right from the beginning, usually we have multidisciplinary teams. You need linguistic stability. The same words need to mean the same thing, otherwise you crosstalk. So I think stability is a really great concept to unify. And I already said about reasonable perturbation. And then if you dig into the theoretical side, that was in my 2013 paper on stability. Central limit theorem, I learned it from kind of a characteristic function, but there's one version. I mean, Terry and Stahl have 7 different proofs of central limit theorem on the internet. One version is called Lindenberg swapping trick, right? You have x1 through xn, and you just swap by IID Gaussian. And then you use Taylor expansion to control the perturbation. In the end, you end up averaging, square root averaging IID Gaussian random variable. You have the Gaussian. The other proofs that you don't swap by Gaussian, you swap with other IIDs, and you say that the law is universal, and prove that you satisfy ODE, the only distribution satisfied that is Gaussian. And if you go to random matrix result, right, you don't see Gaussian anymore, but you see this perturbation argument. And uniform stability has been used in machine learning to bound generalization error. So all of that is really stability. And on the ground, as I will showcase some case for the last 10 years, we really find these general principles really, really helpful to guide us. For me, of course, I thought about these things, but I was not systematic using these principles. So sometimes I use it, sometimes that. So really streamline our own thinking in solving really data science problem with domain experts. And every time you have to do something different, but the principles stay. And just writing something while I was in Sanjit's talk, right? I think the principles actually unify many aspects of Trustworthy AI on his slide. Reliability, I think there has to be like some reality check, and also means kind of stability. For me, reliability. And robustness definitely is stability. Transfer learning is a particular perturbation, it's also stability. Fairness, you look at subgroups, again, stability. And differential privacy is a form of stability. So PCS is really coming from the practical side. It's a prerequisite for trustworthy AI and also for AI alignment. It's not everything. We definitely don't do hardware, but I think the principles, how can you argue against reality check and stability, kind of reasonable arbitrary human judgment calls? And computation, of course, we all do that. So now stability principle had 2 roles. First, find reason perturbation, document it, and assess. The second, if it's not, the assessment related to specification in a way, what's good enough for the assessment to pass? And then when it's not, what can you alter the process to improve, to make the specification or requirement satisfied? Like in his simulation, you do revise the deep learning algorithm and you reduce the kind of mistakes a system makes. And then people often ask, how do you choose perturbations? Documentation, context, and human knowledge, and resource constraints. And there's around the same time, my stability paper, there's a paper from all the Bayesian colleagues, Gauman and Larkin, they call the garden of forking path, right? So they recognize that there's all these human decisions, but mostly in the modeling stage, but they don't provide principles to say, how do you cut some of the forking path? Yeah.
Just a clarification, can you remind us what is DSLC?
Data science lifecycle.
I see,
Yeah.
okay.
Data science lifecycle. Yeah. So feel free to ask questions. Yeah. So documentation, documentation, documentation. Do you see a Golden Gate Bridge, the bridge in there? You're imagining it. You see the post. The bridge is under the fog. So you really have to build a bridge from models, which I think is a mental construct, to the reality. And that's where the documentation comes in to serve. And we have a template for people to lift and revise for their own purpose. Yes. Yeah.
Thanks. Can I ask a question on the previous slide?
Sure.
So I'm trying to understand. You have these different weights where you say, well, based on prior knowledge.
We haven't done that.
But do you need kind of stability in those again? How do you reason, even in documentation, that the weights you're using are somehow reasonable?
You cannot remove human judgment calls. So you do the best you can and make it transparent. We haven't done any weighting. We basically have just do marginal perturbations. But perceivably, a committee can decide what's a reasonable weight. That's just expert systems. Right? Even smoking caused lung cancer was a human committee decision. In 1963 or something, they look at 2,000 observational studies, and the NIH committee made the decision is causal. So I think we cannot remove, but I try to be transparent and at least perturb something than what we do. It's not like a 100% proof thing. It's more nudging us to the right direction.
So how do you deal with the problem of, so I can see how in data science, right, we can verify because we have truth. But when we move to trustworthy AI, where truth may not be present and experts may be noisy, as you've shown, right, 73 teams of scientists come with different conclusions. Right. How does that come into?
At least just the transparency. So people.
Well, how do you deal with the fact that you may be in contexts where there is nobody in the room knows what the truth actually is?
Well, I think we should report that. Honestly, just report that we don't agree. So the public decision should be a political decision. That's what expert cannot agree. But as mayor or a governor might have to make a decision.
I'm thinking of an autonomous vehicle, right?
Yeah.
You have different algorithms or different sensors, and some are telling you that there is a pedestrian on the road and another one isn't.
So I would take, in that case, the most conservative approach. Right. So it depends on the context. But first, just at least acknowledge.
Just following up on that comment,
Right.
you know, that couple of years back where there was this pedestrian who was killed. I don't know which one, in Arizona or someplace. I think that from what I remember, I had read the report, but I don't remember all the details, is that there is also a timing thing in these autonomous, which is missing here. So I think it was not that the system didn't recognize that there was something weird going on. It was too late in actually giving it to the driver. So which is missing, like in medical, probably it doesn't matter if the doctor is maybe 30 minutes late, it's I guess fine.
Yeah,
but in autonomous thing, I think there is a time aspect also.
which is the C part. You're right.
See,
Computability, whether you can really compute fast enough. And you're completely right that so far we have not incorporated C as intimately as we could, because all the applications, all the problem we work on, C just not as demanding as autonomous vehicles. But we're working on ER with ER doctors, right? So they're going to come in at some point. But you're right. We haven't dealt, we have been doing more offline computability simulations, but this dynamic setting, we haven't really had a case study to do that. But I think will come when we really get deeper into the ER room, because there things happen very fast too. Yeah, but you completely right. Yeah, it's there, the C, but we just in the case studies we haven't have to face it so timely. Yeah,
I have a question on the PCS documentation. So that sounds like it's a form of specification of the process that's being followed.
Yeah.
Do you have examples for us on what that looks like?
It's on my website. So every paper we write now, we have a PCI documentation.
I see, because I think that could be an interesting point of connection for the formal methods and related communities to think about how to formalize that and then build tools to help you check that as you go.
Because a lot of the data analysis, people are now pushing for automatic data science.
Yes.
So that's, we're still kind of holistic in a way, but we're going more and more formal in a way. So I think this is a great opportunity.
Great.
Enough that you asked that, because this is exactly what I'm also checking, documentation from your slides.
Yeah.
And you say documentation, it's narratives and codes to explain assumption and justify judgment calls. So when you say narratives, to me that sounds you provide some examples, or you provide English language explanation.
So both. So we have a template you can fill in your problem. For all the papers you write, like cardiology, we have sample documentation too.
Mm-hmm.
So both. So for all our papers now, it comes with a PCI documentation for the relevant ones.
Yeah. Can you just, sorry for that. Maybe just to kind of, because this is something I think that formal methods and synthesis community would be very interested. Like maybe just can you give us a very simple example without them, you know, like.
So for example, for the prostate cancer example, I'll get to, right? Maybe I'll say there. Yeah. So just maybe I'll get to it. Yeah. So we're there. And the multiple rows we have, it's really try to push the internal validity as much as we can. Do all the perturbation instead of just the minimum. What happened? Something dropped. Yeah. And then the other is for causal inference. So causality, I will mention it, it's a lot stronger than predictability and implies also stability and predictability. And we become a recommendation system. Want people do experiments. And we also redo some analysis for clinical decision rule. That's a stress testing, follow these principles. And we can also do new machine learning algorithm I'll get to. And a couple of groups already extended this framework for reinforcement learning by Susan Murphy School and Tianjin to network analysis and so forth. So here are a few case studies, right? I will speak about this too. So this is clinical trial data. We try to use this principle to find subgroups. A particular painkiller will be beneficial for this subgroup. So the drug Vioxx was pulled out by Merck after approved because there are two side effects. One is a stomach problem, the other is a heart problem. So we say, can we find subgroups that only benefit? And there we're facing a problem, multiple algorithms. So there's something in causal inference called heterogeneous treatment effect estimation. It's very much related to precision medicine. You don't want to say on average, this drug is good. You want to say for specific groups that you have improvement. And for that, there are many methods. In the paper, we consider 18 different algorithms and say, how do we consolidate and aggregate to reach conclusions? And this one I'll get to, so I want to say more about cancer detection. This one is about cardiology. The Stanford cardiologists did experiments. And this is a new paper with Alec Hoos, who's joining neuroscience and statistics July 1st, and really try to find new brain areas about speech. So it has been really mostly in biosciences. So let me get to the prostate cancer example and then case study. I will say a bit what we put in the PCI documentation. So this is, I started engaged with cancer research right before the pandemic. I gave a talk at Hutchinson Cancer Center, and the Cancer Center validation director Zhing Feng really liked the framework because he was facing that. So his job was to reproduce the data and try the algorithm. So it's a validation. He has a validation center. So many of the biomarkers for cancer, people published papers and he couldn't replicate. The replication was pretty low. And so he thought this could help, but he said, you know, my PI is not going to listen to me. You have to do case study. So he did case study with MD Anderson Center, Sam Hanash group for pancreatic cancer. And then I was invited to give a keynote for cancer research, early cancer detection network. I said, I wanted to go in with more than one example to convince people to use it. So he introduced me to Aru Chennaiyan, who is a Michigan oncologist, and they already had a paper on arXiv in 2023. And they have something called My Prostate Cancer Score 2.1, 2.0, because I have 1.0. So my two people start working with them. Tiffany is now at Notre Dame, assistant professor. Anna is at UCLA. And Yuping was the data analyst. So we went in stress test their algorithm. So the data to use is family history and gene expression. So this is the new omics. And they already have a validation that's in medical research. You always do external validation. It's kind of transfer learning. That's already there. And they look at the most severe prostate cancer. So prostate cancer is like breast cancer for women. Over a lifetime, there's about 12% chance a man will get prostate cancer. And they got really big lift from what they have. And they use logistic elastic nets, L2, L1 panelized least squares. They end up with 17 genes and plus this gene. KLK3 is the gene that gives the protein the current popular clinical detection PSA uses. So they just put it in, right? And Aru also has a startup. So try to make it to clinical. So what they have seen is that for their result, they want to reduce the people who are sent to biopsy unnecessary because it's very painful. Supposed to biopsy for prostate cancer. That's where you get the biosamples to verify it. So it's a huge lift compared with previous methods, 21%, that's current standard, 15 and 7. 7 is from their own method. And they use 18 genes. So we want to talk to Yuping and then say, did you process your data, right? Because we want to look at data cleaning. She said, yeah, of course, I did some thresholding. And then we asked her, could you have done something different? She said, yeah, I could have done something different. And asked, what are the other ways you could do that? So we agreed she would try 3 other ways. She said, I could have just done that. There's no reason I did the way I did. So we added 3 more cleaning methods. And because we could do more, but time constraint, energy constraint. And then we follow the PCS framework. And we introduce more methods because why elastic net? Why not ridge regression? Why not lasso? Why not simple deep learning? All of that. You could have used it. Yes.
In this context, what is the P? What is the check you did there?
The prediction check on the validation set.
Oh, I see.
Yeah.
So this is evaluating the sort of the traditional metrics of accuracy or
this is
on the validation
yeah,
set.
this is the accuracy.
Okay.
Yeah.
Thanks.
So here we did, right? So you see this block of lines. This is what she did before we joined. This is 3 other ways. I won't give detail. Just she said we could have processed other ways. And this is logistic elastic net. And this is some bootstrapped intervals on the AU, it's actually AUC, area under the curve. And you can see they're more or less aligned. And we said, why not logistic ridge, logistic lasso? And we have a new method called random forest plus, so on and so forth. So each block is one method and 4 different processing. And then we have a new method, which is only on trees, definitely doesn't work very well, called fix, so that's deleted. And this one doesn't really have importance measures, these 2. So for interpretation, we deleted. So we end up with 6. So instead of 1, we end up 6 methods seem to work just as well. That's it's a hyperparameter in how do you cut for the prediction check. And then we basically end up with something we call PCS ranking. We think it's a more trustworthy way to look at the importance. So all these measures of importance are different, right? For linear method, we use the coefficients. For random forest, there's something called MDI. They're not scalable, but the ranking is comparable. So what we did with 6 good methods, we ranked all the genes among the 54, and we took the average rank. And then we basically rank all the genes. So the documentation will be, you write about the data you have, what the problem you try to solve, and then write about why we did all these measures and all the codes, and then the new method, and then a conclusion. So that's a simple PCS documentation. And then we end up also use a clinical variable they also did. So they have been trying to reduce from 18 genes, but with logistic regression, because if you know the linear method, the dependence really are mixed up with what's important or not. So when you use multiple methods, different methods still have to deal with the dependence, but they do it in different ways. So that kind of break some of the sole dependence, become more trustworthy. So we end up able to go to 7 genes from 17. We also keep the original gene, right? Because that's what's being used. And they're all known prostate cancer genes. We call simplified MyScore2. Oh, actually, I should update that. So the paper just got accepted into cancer biomarkers. And on external validation, whereas the S, you can use 7, you can use 8. So this is the 2. And you lose a little bit, like 1%. But remember, data cleaning will introduce about 1–2% difference. Therefore, we think it's within the error. And this is with prostate volume, so you can get a little bit better, but usually you don't always have the prostate volume. So you can see both comparable. So then Aru invited us to join a new patent application for the simplified MyScore, MyProcess2. It's a joint file with Berkeley and Michigan. And I think his company has exclusive right to develop into a clinical test. And they have to run clinical trials, all of that. So to summarize, if this works, compared with the original MyProcess2, we reduce from 18 genes to 10, to actually 8. So it's a more than half reduction. Each gene probably costs $20, $30 to measure. And we think, or I think, because the stability, the different methods kind of good experts agree, they are more likely to be causal than the 18 ones. At least you reduce the scope for further up studies, and people could run studies later to follow up on that. And this methodology, of course, is not just for prostate cancer. For any other cancers, you can use the same thing. We have a pancreatic cancer paper with MD Anderson group. So far, stability is used more holistically. You just decide what method and you come up. So next, I want to talk about uncertainty quantification. I think I'm running a little long on time. So I'll just give a very quick view. So in the chapter 13 of the book, we published, because there's a free version, and this is the book version, came out October, MIT Press in the machine learning theories. We actually went for uncertainty quantification, so more formal. So far, stability principle, we just did it holistically and have something sensible come up. And Rebecca was my co-author, and this is a team of people who are working with me. Abby is great PhD student, Michael, master student. So let me just go quickly, since I'm not, like give you a summary. So what we try to do in the book is that this is bootstrap mostly. People can do that. You can do asymptotic normality. Data cleaning, we added, and we want the pre-checked modeling. And for the result, I'll show you, data cleaning is actually very tricky. So the data I show you won't have that part. But in the book, we have only 2 data sets, didn't compare with anything. In spirit, the quantification is very much like bootstrap. Bootstrap doesn't matter you end up with a discrete set of pseudo data sets saying that you could have observed. So in that spirit, we're doing the same thing. And how we do that, we allow that, but the data result won't have it. We use multiple algorithms called candidate algorithms, and we eliminate the bad ones. That's a Harper parameter, like top 10% of how you find a gap. And then we do a multiplicative calibration on a validation set to get the right coverage. And so conformal, probably you all have heard about conformal, right? Has been quite a big study from the theoretical end. And the exchangeability, there's validity. But the question, the size of the intervals are not really addressed. So that's what I think it turned out like we had a lot more data. So comparison, they use one model And we chose the best one among the candidates to be fair to conformal when we compare. They don't do model checking, at least not the vanilla ones. Some of the recent ones might be doing that, but they use a fixed kind of way to calibrate, use residuals. And both try to deal with model misspecification. So experiments. We collected, let me just go, 17 real world data sets. We try to find data sets mostly without missing values, because how you impute will make a difference. We think might be unfair to one versus the other. So we mostly find clean data sets. And this is from different sources. Yeah.
I think we need to speed up.
Oh.
We have a little bit of cushion at the end. So
Okay.
if you would like to cover this, it's fine if we go a few more minutes
Okay.
into the break.
Thank you. Yeah. So here's the takeaway. They both calibrated, so they have desirable coverage. And on average, we choose the best conformal because they only use one method. We have a candidate set, so we choose the best one among the candidate considered. We reduce the size by 20%. And they have a studentized version. They should try to deal with heterogeneity. And for subgroups, we do better coverage. And we still better than the studentized, which deal with heterogeneity. So let's just look at the 17 data sets, right? So you have the orange is PCS, magenta is split conformal, blue studentized conformal, and majority vote. Majority vote doesn't do data cleaning, do have many candidate model. You can see that if you want to consider multiple ML measure, you have to do model checking.
What is the y-axis?
The y-axis is the mean width, the size of the interval. Yeah, and we standardize, that's why between 0 and 1. So first, the green one, you need to do screening. And for conformal, you can see that depends on different data. One might be better than the other. But the orange, ours, is consistently the best. This is more summary, the reduction of size of the width is that we reduce about 20%, and the majority just not very good conformal. And as I said, precision medicine, you need to look into subgroups. So some of the data set have a discrete predictors, which is split on the discrete. For the ones we don't, we look at the one-dimensional predictor and find two modes and split that way. And you can see that this is the average. We all hit the 90%. And this is somebody with low income, the group, and high income. And the orange is PCS way of doing it. We adapt to the signal in the subgroup, sometimes bigger, sometimes shorter for this group, but all smaller than the conformal. And you can see that the split conformal doesn't reach the coverage for the subgroup. So we didn't a priori decide the subgroups. So there are some methods that if you know the subgroup, conformal can adapt, but this is post hoc. The reason is because in some sense, when you have small beginning intervals, when you have lots of data, usually the interval is small. When you do multiplicative calibration, you keep that. But when you do constant enlargement, you lose that. And they don't do bootstrap, we do bootstrap. But that costs, we'll mention about computation efficiency. So that's another data set, it's the same behavior. And then we generalize, the book doesn't have a multi-class. So the new work with the new group of students, again, we have 6 tabular multi-class data sets, and we again reduce by 20% of the size. So here, you not looking at probabilities, we have binary classification. When you have multi-class, the conformal people have been doing, give you a set. Actually, it's more informative. When you have 100 class, you don't want to see 100 different probabilities. You just say that's the set. So we follow the same thing. For binary, we actually have a probability prediction. Yeah.
Question. So just to compare conformal versus the PCS approach, is there anything in terms of the assumptions like exchangeability made by conformal? What is Is there something on the
So
PCS side, or
the
are they
PCS
equivalent?
come from the empirical point of view,
Okay.
right? So we have a result now showing that you can do, and the extendability, you also have the validity.
Okay.
But it's a very different development process. Conformal mostly come from theory extensibility.
Right.
We come from the empirical side.
Okay.
That's where I am. And now I look at theorem. I want to see, that's what machine learning took off too. It's actually empirical deep learning the same way. So a lot of the most statistical methods useful really come from the empirical end. You see it works,
Right.
and now I do theoretical analysis. And now I want to do multiple theoretical analysis. So it's
Okay.
very different development phase.
Okay.
Yeah. And there's not, we become, when we finish the paper, the largest empirical study compared with conformal. People have very few data sets in their conformal paper, 1 or 2 or 3 or something. So there's no systematic, even between different conformal. We become the only like the largest systematic, even compared different conformals. So this is a different conformal methods. And you can see that the number of classes relatively large, and the sample size varies. So for tabular data sets, we just chose the most popular one. People seem to think works, right? But again, we compare with the best one for conformal, to be fair. For this, we have 5 out of 6 data sets. We perform better. There was 1 data set where we're a little worse, but on average, we still reduce by size, the set size by 20%. And for, I missed some slides about, so for deep learning, Bootstrap is too expensive. But for 2 speed up, we basically fix deep learning, you have to fit at least once, and just add white noise to the weights to get multiple models. The size of the white noise is just when you train the model, you have initialization random noise, we use the same. And that reduce, again, we do better about 20%, and it's a comparable computation with conformal. I missed the slide. So the theory is that we now use training more, we get better result in experiments, but to do theoretical analysis, you want to separate the training to do the screening and do the validation. So when you do that, we can show theoretically like same validity. So it's actually a new form of conformal analysis. Yeah. Again, came from the empirical side. The reason I was convinced myself to put a chapter into the book without doing enough data, usually it's not my common approach, is because I really trusted the framework. You have so many success stories in other related areas, but not for uncertainty quantification. But it panned out. It was a bit a gamble. Yeah.
So on the issue of conformal prediction, so there is another way to go empirically with this, which is that if you're able to evaluate noisy experts, right, you have their decision tuples, and then you can sort of map them right onto, well, if I choose this label, you know, this is how many would be correct, and this is how many would be incorrect. So I just wanted to point out that just through evaluation, not using anything about decision, we can also create empirical conformal measures.
Yeah, so I just haven't seen the literature people do relative life cycle comparisons. So that's the first we have done, try to compare different conformal and with us. So to summarize, the PCF is really try to constructively respond to the reproducibility crisis. And I showed you the reduced cost of prostate cancer detection. And mostly our method are from existing conformal method. There's a new form of conformal. And the question is, how can we certify this time life cycle? I think PCS with documentation is a formal empirical certification or verification. And there are multiple approaches that follow PCS with documentation because people can exercise different reasonable judgment calls. Therefore, the certification is now unique. And it's kind of open system, but hope the data conclusions are in agreement in most cases. If not, I think we need further evidence. This is a very open system. It's not closed, you can say things, but I think a formal analysis, a documentation, all of that would be really helpful, especially people really going to automated data science right now, right? I think Google pushed something called automated data scientists and even automated scientists, all of that. I think some formal analysis and we combine with empirical results. So I think I should stop here before I go to the next one. Yeah, thank you.
All right, so we're running about 10 minutes behind schedule. So we'll take a break now and we'll reconvene at 11:10.